Howdy, y'all. Uh, Welcome to another session of Chem 119 lecture videos. For any of you that are newly switching into my class, this is all the contact information that you might need. So my name, my lecture time, and the Zoom link is on eCampus. My office hours, again, the Zoom link is on eCampus. My office, I'd prefer if you use Zoom, just because that's university policy. But if for some reason you would like to talk in person and it feels more comfortable, feel free. We don't have to use my office hours. If you need to talk privately, we can set up something else. Just let me know. My email, our course site is on eCampus. It's going to be the one that has these section numbers here at the top. And it will also have my name at the end. That is our lecture eCampus site. So that is where you'll find everything you need for the course. And if you're new and you haven't met them yet, our course IA and SI leader. So we have our IA, Nick Schuber, who is a graduate student, and our SI leader, Austin Bond, who is an undergrad like you, did 119 a year or two ago, so very recent alum of Chem 119, and he can help you with problems from a more, I don't know, peer point of view. So this is their contact information if you need to email them. All right, so reminders, Chem 119 labs start next week, the week of August 31st. You don't need to purchase the lab manual or course site until then because it's not available. So just wait until you have your first lab and we talk about the course site in that lab meeting. If you are new to this section, make sure you log onto our eCampus site and read the syllabus and the documents for getting started. So we have getting started with ALEKS. You'll have to switch into my ALEKS section and my code for the class is in that document, getting started with ALEKS. And then you'll also have to add my REEF class. That code or that class name is also in those documents. So guidelines for REEF polling is that one. There is an introduction assignment on eCampus, which is due on Friday. If you're new and didn't know that, everybody else, it's a reminder. If you haven't done it yet, please do so. You go to the participation questions section, click on that, and then the assignment description will come up, but make sure you click on the link for the assignment. So where it actually says introduction assignment, that's a link. Click on it and you'll be able to attach your document in there. Just another reminder, if you are new to the class, you will need to do another initial knowledge check. If you came from a different section, I apologize for you having to do it again. And we had homework due on Sunday, and there's some homework due tonight, Tuesday night. So that is the Chapter 1 homework. So if you missed that because you switched into the course late, let me know and I can extend it for you. Otherwise, a few homework points aren't going to make a big deal. And our next homework will be due Thursday nights, and that'll be on Chapter 2, which is in this video. There was a little bit in the last set of videos, but this one is going to be all Chapter 2 stuff. Cool. All right, so let's talk about some new stuff. So this is something we call an atomic symbol or a nuclide. I don't know why they call it that, but you will see both terms in your textbook, atomic symbol or nuclide, so you know what that means. So the way that this works is you have the elemental symbol here. So we can look down here at this example too. This is titanium. This could be anything. It could be carbon, could be oxygen, could be nitrogen. It's the elemental symbol for whatever element you're talking about. Carbon is C, oxygen is O, nitrogen is N. Make sure you check out the periodic table and learn some of those common symbols for our different elements because I won't always give them to you. You might need to know what element I'm talking about based on just a symbol. Usually they're pretty similar to the word themselves, but sometimes they're not. So iron, for example, is Fe. That's not really that well known, I guess, but it comes from the original name. So it was like ferric. Ferric or ferrous are different ways we talk about iron compounds. So just so you know, sometimes they aren't very similar at all to what the word is. All right, so X is the element symbol. A is our mass number, and Z is our number of protons, the atomic number. So I'm going to start with Z. So if you look at the periodic table, you won't see it written like this, but you will see a box like this. It'll have a number in the corner. Sorry. Say we have number 6, that's carbon, and then we'll have something written down here. So that is what it looks like on the periodic table. So this is carbon, and the number, the atomic number that's in the upper left corner, that tells you the number of protons that that element has. So every atom of that element has that number of protons. So every atom of carbon has 6 protons, always. That's indisputable. So that's the atomic number. So you'll find it in the upper left of the periodic table box, or you'll find it in the lower left for these nuclide symbols. All right, so mass number then is the sum of the protons and neutrons. So it's not the number of neutrons. You can't just pick it out that easy. It's the sum. So if you want to know the number of neutrons, you have to rearrange your equation to be A minus N, or sorry, A minus Z, or P. So if you do A minus Z, A minus the number of protons, that will give you the number of neutrons. So the bottom number, the atomic number, tells you exactly the number of protons. You don't have to do any math to figure that one out. But the mass number tells you the number of protons and neutrons. So you do have to do a little math to figure out the number of neutrons by themselves, okay? And then finally, in a neutral atom, the number of electrons equals the number of protons. So however many positives we have the same number of negatives to balance it out to a neutral charge, okay? So the atomic number Z that you find is going to tell you not just the number of protons, but also the number of electrons in a neutral atom. Note that I denoted that fact that it's a neutral atom. We will talk about ions in the future, but for now we're just talking about neutral atoms. All right, so let's look at an example. Sometimes they don't give you this number that's down here. Sometimes you won't see that, and that is because that number, the atomic number, you can find on the periodic table. It's always the same for that element, so because it never changes, we don't actually need to write it. So I looked up titanium on the periodic table, and I found out that the atoms of a titanium element always have 22 protons because titanium is atomic number 22. This is a neutral atom. There's no charge over here, so the charges go on the upper right side. If there was a charge, it would look like this. But there's nothing there, so there's no charge. So that means protons and electrons are equal. And now we just need to find the number of neutrons. So A, our mass number, is 48. So it's going to be 48 minus 22, our atomic number. So there are 26 neutrons in this nuclide. So we've got 22 protons, 22 electrons, 26 neutrons. All right, cool. Let's practice some. All right, so I have this blank table for you guys. You can practice on it. So I would pause here, write this down, fill it in, and then on the next slide, I'll show you the answers. Okay, so make sure you try it before you look at the answers. Feel free to pause right now. Okay, all done. I'm glad you practiced this yourself and filled out this table. These are the answers. So we have chlorine with 17 protons and electrons, calcium with 20 protons and electrons, vanadium with 23 protons and electrons, and finally plutonium with 94 protons and electrons. And the neutrons are there for you to figure out from the mass numbers. Cool. All right, so I'm glad you practiced that. That will be on your homework. So let's talk about the periodic table a little bit. So what can we learn from the periodic table? So, like I said, the atomic number is on the periodic table. That tells you the number of protons. Sometimes you'll see the mass on the periodic table as well, like here. It's kind of hard to see, but the atomic mass is down at the bottom. So for nickel, for example, we've got 58.693. There we go. And that is going to be in atomic mass units. So we learned about these a little bit in chapter 1 if you read the textbook. Atomic mass units are how we weigh the protons and neutrons. They're really, really, really tiny. So we use atomic mass units. Sometimes we call them Daltons, but you don't need to know that really. All right, so that's what you can learn from the periodic table. If you pause and take a look at this slide, you can tell that you actually learn a lot more about from the periodic table. This periodic table, for example, has the names of different sections of the periodic table color-coded. It also has the names of all of the elements below their symbols on this periodic table. So it's really nice. Depending on which kind of periodic table you look at, you can get a lot of information. So I know on your homework, one thing that they might ask you is to find some element that has atomic number less than 60 that weighs more than let me try and make a good example here. Atomic number less than 44 that weighs more than 90 grams per mole, or 90 atomic mass units. So less than 44, so it's to the left of ruthenium, and then we look at the mass. So the mass is that bottom number. And all of those are greater than 90. So those are your answers. They might want you to write how many elements that means. They might want you to write the elemental symbols for those elements. But that's a type of problem that you will see on this homework. It's reading the periodic table, looking at atomic numbers and mass. All right, so we learned a little bit last time about how Dalton came up with this theory of his atomic theory, where he said that all atoms of the same element are the same. That is not true. It was definitely very likely back then, before they could do the types of experiments that we do now. But knowing what we know now, we know that atoms of the same element can be a little bit different. They can have a different number of neutrons, which means they'll have a different mass number. And we call those isotopes. So, for example, our isotopes here are uranium-238 and uranium-235. And some isotopes are more abundant than others. The abundances are written down here, where it looks like or it looks like uranium-238 is blue and uranium-235 is red on this pie chart, because uranium-238 is 99.2% abundant, whereas uranium-235 is much, much, much more rare. You only find 0.72% of uranium-235 in nature. Most all uranium that you find, if you would take some out of the ground, is going to be the uranium-238, which, lucky for you, uranium-238 is the less radioactive of the two. It's not the one that's used in atom bombs, so cool. It's good that the, dangerous one is the one that's rare and not the safe one. So isotopes, once again, have the same number of protons. They have the same atomic number. So there's no atomic number written here, again, because like last time, I mentioned that that all elements have the same number of protons or the same atomic number. So that means we don't have to write it every time because it would be the same. And you can just look it up on the periodic table. But we do write the mass number because that's not always the same. It's different for different isotopes. All right, so how many neutrons are there in uranium-235? So uranium-235 is this one, which means its mass number is 235. So A, our mass number, equals 235. And the number of neutrons, remember, is A minus Z, A minus the atomic number. So you have to go to your periodic table to look up the atomic number of uranium. And I did, and it is 92. You'll find uranium pretty much kind of in the middle, all the way at the bottom of the periodic table. So 235 minus 92 will give us our number of neutrons, and that is 143. So uranium-235 has 143 neutrons. How does the number of protons in the nucleus of a uranium-235 atom compare to the number of protons in a uranium-238 nucleus? Let's think about that. So what did I tell you about isotopes? They have the same atomic number, which means they have the same number of protons. They are, equal. Always. The number of protons in the nucleus of an atom of one isotope are always equal to the number of protons in the nucleus of a different isotope of the same element. Don't get that confused. Neutrons change, protons don't. All right. So just so you get some relevancy about isotopes, so uranium, natural uranium, like I said, which comes in the form of this uranium ore, is mostly uranium-238, which is the safe one. It's not used in nuclear weapons or nuclear energy. There are safe, well, not safe, but there are non-war based uses for nuclear chemistry as well. Don't think that I relate nuclear chemistry to weapons all the time. It's not true. There are useful, beneficial uses for nuclear energy, and that would be like nuclear reactors, nuclear energy. So they take that uranium-235 and they enrich it, which means they get, they increase the percentage of uranium-235 found in their sample. So now we have more uranium-235 and we keep enriching it to get a higher percentage of uranium-235, which is when we call it weapons grade. So we take out the natural uranium-238, we take that out, we take a little bit out at a time, we get to here, and we take out a lot, and we get to here. So when you take out that, the percentages shift. The percentage of uranium-235 goes up, percentage of uranium-238 goes down. So that's what they mean by enriching the uranium. So nuclear chemistry is really cool. You might learn a little bit more about it in Chem 120. It's an optional topic in Chem 120, so it depends on your instructor. But basically what happens is they shoot a neutron, they fire a neutron using an atomic collider. They fire a neutron at a uranium atom, in this case the 235 isotope, and that causes it to split apart into smaller pieces and some other neutrons. And if there are many different ways that that can happen. And then it keeps going on and on, because you'll probably have more than one atom of uranium in your sample. So if you hit one atom of uranium with a neutron and you get one atom, in this case of krypton and barium, then neutrons are released in that reaction, which cause a chain reaction by hitting more atoms of uranium and making more atoms of krypton and barium. So this is what we call a chain reaction or fission reactions. All right, a little bit more like relevancy about isotopes. The ratio of stable isotopes is unique for certain things. So for example, it helps people follow migration routes of different birds or different fish. It helps people authenticate items by making sure they have the predicted ratio of stable isotopes in them. So there was something coined by a now famous Texas A&M professor named Jason West. He coined the term isoscapes to describe using land maps or heat maps to talk about the ratio of isotopes that is used for different purposes like this. So it's pretty cool. Pretty cool to see the real life applications of our chemistry, right? Another example of isotopes in real life is carbon-14 dating, which you might have heard about. Carbon-14 is an isotope of carbon, and it's extremely scarce in the environment, and it forms carbon dioxide with carbon-14 in the atmosphere, which is taken in by plants. Animals consume those plants, and then animals have a certain ratio of carbon-12, carbon dioxide, and carbon-14, carbon dioxide inside of them. But when they die, the carbon-12 remains because it has a really, really, really long half-life. The carbon-14 starts to decay with a known half-life, and we can look at the ratio of carbon-12 and carbon-14 in the living thing, monitor how it changes over time, and compare that to the half-life of carbon-14 to figure out how old a certain fossil, for example, is. So pretty cool. So I hope I hit a few of the different things you might be interested in: nuclear chemistry, forensics, archaeology, geology, different things like that. So I'm going to stop here and we'll go on to the next video.